Okay, so we're starting our unit on discrete probability distributions. And as a result, it'd be a good idea to have a little bit of a background explanation as well as to hear my voice on a few of these ideas. I've already got notes for all of this all settled out for you with little annotations in different colors left and right, scanned and set in there, but this video may help you out a little bit more as well. So a probability distribution, first of all, is basically you take all of the possible things that could happen, no matter what it is that you're looking for the probability of, and then you sort of see how each probability event adds up to the total. Okay, because in a probability distribution, you're going to see everything, the probability of everything. It's very much like a relative frequency histogram or bar graph, in this case a bar graph, because it's for discrete variables, but it's very much like a relative frequency figure in that a relative frequency is an amount out of a total. The only difference is for discrete probability distributions, they aren't just experimental or empirical, they're going to be distributions that are based on theoretical probability. So anyway, we'll just go through this whole idea. Now there's a couple of ways in which we communicate these ideas, okay? But before we do that, we want to talk about something called the random variable x. The random variable x is basically what the outcomes could be. So here the random variable x is written as x, of course, and p at x equals x is the probability of that random variable x, okay? And then you look at the probability of specific values. It's just a different type of a notation, but it's using the p bracket notation like we did in our probability unit, but we're also saying it's like a function. P at x is equal to something, whatever it may be. And in this case, for discrete, it's going to be discrete variables. So it's going to be situations where only specific numbers are allowed, or I guess it could also be categorical. Categorical are also a type of discrete data. It's just they're non-numerical, so there's only certain ways you can go about doing things with them, and you can't do some of the benefits of these probability distributions, which is something called an expected value or an expectation. So first of all, how do we, just an example that I have here, p at x is equal to 6. I'm looking for a specific case, for example, a rolling a 6 on a die. So the random variable x is the rolling on the face of the die, or the number of pips on the face of the die. And then the 6, of course, is the outcome that we're looking for in this case. Now, that's not the whole distribution. I'm just looking for the probability of one specific event. Okay, so a probability distribution would be all of the rolls, all of the possibilities, from 1 all the way to 6 on a 6-sided die. So if you see here, we've got this first way we communicate it, which is a probability distribution chart. And the way that we see it is, these are my outcomes. My outcome is sort of the value on the face of a die. In this case, 1, 2, 3, 4, 5, 6 are all the outcomes. Discrete values, you can't have a 1.5 or a 2.2. And then the probability for all of them. Now the probability for all of them is 1 out of 6. And you could, of course, write that for all of them, or of course 0.17 if you want to abbreviate it or approximate it, but writing it out 6 times is not really important. This is in fact an example of something called a uniform probability distribution. Now this category here, or this empty sort of part of the table right here, that's going to correspond to something we're going to do a little bit later called an expected value, and that's where we will do calculations that will help us figure out specific expected values for a situation, and I'll talk to you about that in a second. We can also communicate it using a probability distribution graph. Okay, in a probability distribution graph, it's just like a chart. The only difference is one is visual, one is just straight numbers. There's pluses and minuses to both, but they both tell you exactly the same thing. One just does it in a visual capacity, and the other one does it just in a numerical capacity. So it sort of depends on what you want to do. The x-axis is always the value of the random variable x, so this is always going to be x, that outcome x. And the y-axis is always going to be probability, or p at x, as what we usually write that as, p at x. Okay, so that's that. Anyway, here's some examples of different types of probability distributions, and we'll be going through these in the next couple of units. One common type of probability distribution is a uniform probability distribution, and uniform just means the same. Okay, so it means that the probability of every single outcome is exactly the same. This happens usually with probability tools and things like that, you know, like dice and spinners and stuff like that, but it also happens in other instances as well, okay, and not as common. All right, and again, this is a probability distribution for for discrete variables, and so you'll notice we have spaces between all of our bars. What you'll also notice is that the probability of every outcome is going to be the same. You'll notice that in the table, probabilities are all the same, and you'll notice that in the graph because the probabilities are all the same all the way across the curve. Okay. In this case, of course, it's the probability of rolling an 8-sided die. We know the probability of each outcome is 1 out of 8, and there are 8 outcomes. Of course, that adds up to 8 out of 8, or a total of 1, and that's important because the probability distribution should add up to either 1 or very, very close to 1 if you're using something like a geometric distribution of probability. Okay. There are, of course, situations where it's where there isn't a uniform distribution. Oops, this should say non-uniform distribution. Okay, make sure you fix that in your notes. Okay, and this would be an example of rolling 2 dice and looking at the sum of 2 dice. The sum of 2 dice is a little different. Okay, we came to understand that because we know the most common roll is a 7. You can get a 7 by rolling a 3 and a 4, or a 4 and a 3, or a 2 and a 5, and a 5 and a 2, or a 1 and a 6, and a 6 and a 1. So 6 different ways depending on what those dice turn out to be. But for the outcome, like for example a 2 or a 12, the only way that you can get a 2 is rolling 2 ones. That's it. There's only one way to do that. And the only way that you can roll a 12, of course, is to roll double 6s. So in that respect, it is, again, the same idea, a fairly low probability. The probability is out of a total, which is 36. And of course, it's 1 out of 36 for an outcome of 2, and 1 out of 36 for an outcome of 12. Whereas for an outcome for 7, it's a 6 out of 36. And it actually forms kind of like this nice pyramid sort of shape when we look at the distribution of the probability, where the extremes, 12 and 2, are the lowest outcomes that are possible, the lowest probability outcomes that are possible. And then the highest is the 7, which is the highest probability outcome as well. So again, another example, visually as well as numerically, where we see those different values and what they're associated with and their probabilities. Again, a distribution is how is all the probabilities spread out over the entire set of possibilities. Okay, kind of like a relative frequency distribution. Now, this is an example of where we would do a distribution table where it's non-uniform, and we would be looking at, in this case, the probability of the outcome of a probability experiment that we have here. So in this probability experiment, we've got 3 yellow, 5 green, 6 purple socks. That gives us a total of 14 socks. Okay, and we're only drawing 1 sock out of a pile of socks. Okay, maybe a laundry basket or something, or in this case, a drawer. Okay, now we know that the least likely is the yellow because there's only 3 yellows. The most likely is purple because there's the most purples, and of course, in between, roughly, is green. So we total this out of 14. So the probability of getting a yellow sock if you're only grabbing 1 is going to be 3 out of 14. Not crazy. The probability of getting a green sock is going to be 5 out of 14. And the probability of a purple sock is going to be 6 out of 14. Nothing insane. When we do a probability graph of that situation, again, this is a quick sketch. I'll have a nicer sketch a little bit or in my notes if you want to check that out. Okay, this would be 1 out of 14 all the way up to 6 out of 14. 1, 2, 3, 4, 5, 6. Oops, 1, 2, 3, 4, 5, 6. To 6 out of 14, so that'll be 2 out of 14, 3 out of 14, 4 out of 14, 5 out of 14. Okay, and then we would graph, of course, the outcomes. Now, in this case, these are categorical variables, which can still be used for discrete values or discrete distributions, but the difference here, of course, is there's no first, second, third. There's no order to these. So again, it's non-ordinal data, or in this case, I don't know, you put it alphabetically or something, in which case yellow would be last, but I'm just putting it in the order that it appears. And then I have it listed in my table. And then, of course, we just draw the probabilities associated with it. And again, I'm going to draw a really ugly graph here, okay? But it's going to be same size bars for each. Okay, green goes up to 5, and I'm eyeballing it here from the side here, so it may not go perfectly up to the 6 or the 5 or the 3, so forgive me for that. But again, look in your notes for a more accurate representation. And here we have another example of a distribution. Okay, and of course we'd have a nice title, and the title will want to have probability distribution of, and then in this case, you know, pulling a sock from a drawer. And again, look on your notes to see a nice beautiful version of this where I've done it properly and it's properly labeled. Remember, this of course is probability, or P at X, and this is the value of my random variable, which is X. Now, variables of course aren't always going to be categorical, they're also going to be discrete and numerical. And as a result, when we have numerical values, we have a new thing that we can do. And it's kind of sort of like an expectation in the sense that what would we expect to happen on average? And the key is on average. So on average, would you expect a yellow sock, a green sock, or a purple sock? Problem is you can't have anything in between. It's not like you're going to blend the stocks together in a blender or something like that, so they come out as a mixture of those colors. But when we have an expected value and we have discrete numbers, those numbers can average out amongst each other. So this is where it becomes quite useful. So an expected value, again, is the average result of either what's called a single trial, which is what we're going to focus on mostly for this section, 7.1 and 7.1, or in the old textbooks 4.1 and 4.2, or new textbook 4.1 and 4.2, and it says right here. 4.3 and 4.4, we're going to do repeated trials in our next couple of lessons, okay, for the binomial distribution of probability that has to do with independent repeated events, and then the hypergeometric distribution, which has to do with dependent repeated events. In this case, we're just going to do one event. So it's an average value for one event. So that's what we're going to focus on. Now, the expected value is a simple calculation, and it's usually best done in a tabular form. Okay, although you can do it separately if you want to. What you do is you take the value of the outcome, and then you take the probability of the outcome, and then you multiply them together. Then you take the value of another outcome, and its probability of that outcome, and then you multiply those guys together. And so on, and until you've taken every outcome, and every probability of that outcome, and then you multiply them together. And then what you do is you add them all up. Okay, so by order of operations, you multiply first, and then you sum or add second. Okay? And so I'll show you some examples of that. Obviously, I'm not just going to give you a formula. So here's an example. It's a little bit weird one. But there are 3 pennies, 2 nickels, and 1 dime in your pocket. So you're going to reach in your pocket and you're going to grab a coin, a single coin. Now, obviously, you can feel for the different sizes, but if you don't feel, if you grab it random or you use a magnet or something like that, then you're going to be able to pull out, maybe not a magnet, but anyway, you're going to pull out different types of coins. Okay? So keeping that idea in mind, what are my possible outcomes? Well, my outcomes are going to be a penny, they're going to be a nickel, or they're going to be a dime. Okay, and for each outcome, it's going to have a probability. I'm only grabbing 1 coin. There's 6 coins. There's obviously more pennies than there are nickels than there are dimes, and so they'll have different probabilities for each. What we're going to do is we're going to figure out what is the expectation of a single trial. Should we get a penny? Should we get a nickel? Should we get a dime? Or somewhere in between those? Now, penny, nickel, dime, that's categorical. But we know, of course, that they have dollar values associated with them, or in this case, cent values associated with them. So our units are going to be in cents. And whenever you look for an expected value, which is what part of what we're going to do, first we're going to do the distribution, then we're going to do the expected value. Whenever you look at an expected value, what you're actually looking at is what's the expected value of the coin, or what is the expected length of a piece of string, or whatever it may be that you're pulling out of a group, or doing whatever you're doing for a particular sample. So focus on what the expected value asks for, in this case value actually in cents of the coin, and then in that case we can go ahead and help us figure out the expected value. So this of course is X, okay, and then we've got the probability of X. In this case we've got 3 pennies, so it's going to be 3 out of 6. 2 nickels, so it's going to be 2 out of 6, and then 1 dime, so that's going to be 1 out of 6. And that's what this extra column was for on the earlier distribution that I showed you. Okay, it was for the expected value. EX, which is, of course, this is going to be X times P at X. And the nice thing is, like we had in our other tables in our single variable and 2 variable stats unit, they're all side by side. So we take the 1 cent and we multiply it by the 3 over 6, and we get 3 over 6. We take the 5 cents and we multiply it by 2 over 6, and we get 10 over 6. And we take the 10, the value of the dime, and we multiply it by 1 over 6, and we get 10 over 6. Now, a lot of people think that, oh, it's an average, so I have to then add them up, divide, but no, you don't do any more dividing. The dividing is already built in with the probability. So all you literally do is you multiply, okay, and this is to multiply, and then you add. That's all you have to do. So if you notice, there's going to be a sum, and we're going to look for the sum value. I'm also going to do the calculation down here. Again, I know it's boring, but it is what it needs to be. So 3 plus 10 plus 10, and I do recommend that you don't reduce fractions, even if they are reducible, like 10 over 6 and 10 over 6 could be in reduced form. It could be written as 5 over 3 and 5 over 3. We're going to want to have a common denominator when we do this, so don't reduce any of these. Add them all up. Add up all the tops. Add up all the numerators. The denominators are all going to be roughly the same. Okay, and as a result of that, or hopefully roughly the same, as a result of that, we're going to have the expected value. Now, what that means is, and this is key, the expected value, which is the sum of x times p at x, is going to be 23 over 6 cents. Or if we take that, you divide it, it's going to be almost 3.83, I think is the actual value, if I remember correctly. 3.83 cents, which means on average we would expect to get, when we drew a coin from our pocket, 3.83 cents out. Now that doesn't make any sense because you get a nickel, 5 cents, a dime, 10 cents, or a penny, 1 cent. But if we were to do it over and over and over again, and this is again a power that we get from finding out what we should expect on average each time we take a coin. Sometimes we'll get 10 cents, sometimes we'll get 5, sometimes we'll get 1. We'll get 1 more often, we'll get 5 sort of as often, but we won't get 10 very often. And in the end, it'll average out to 3.83. So it's basically like a weighted mean for probabilities. Okay? Again, for the expected value, we take the x times the p at x, 1 times 3 over 6. Now, you don't have to do this twice. Okay, if you've done it in the table, you certainly don't have to do it again, but this is just a way for you to see the value times its probability. Times its probability, and then the value times its probability. 10 times 1 over 6. You add them all up, 3 over 6 plus 10 over 6 plus 10 over 6 adds up to 23 over 6, or 3.83 cents on average. Now, what this allows me to do is if I pick a coin and I do it 10 times, if the expectation is I take a coin out, look at it, see its value, put it back in so that I don't change my probability of my coins, and I do this over and over and over again for some weird reason, then what I end up having is basically the value after 10 times is going to be 10 times 23 over 6, or 10 times 3.83, which is going to be 38.3 cents. So if I was to do this 10 times, I should expect to get 38 cents out of my pocket. Not that you would do this, but again, this is just a modeled situation so we can understand what it's going to mean in a greater scheme of things. Okay? Here's another example of an expected value and how it's important. Gambling expected values are everywhere. If you ever watched that TV show where they have all the briefcases, Deal or No Deal, it's all about expected value. The banker comes back basically with an expected value and they adjust it based on how much money they want to spend or not spend on the game show. But it's based on this idea. So if you watch that, there it is. So let's look here. Okay, so I challenge you to a dice game. Here are the rules. If you roll a single die and it's a prime number, okay, prime numbers, in this case 1 is prime. 1 isn't prime, but we're going to use 1 as a prime number. So 1, 2, 3, or 5, then I pay you that amount, whatever that is. Okay, but if you roll a composite is a number that has 2 factors that are not 1. Okay, so 2 times 2 is 4. Okay, or 2 times 3 is 6. So in other words, a composite, which is 4 and 6, then you pay me that money. Okay, so if we do it from your perspective, that means if you roll a 1, it's got a value of plus 1. If you roll a 2, it's got a value of plus 2. If you roll a 3, it's got a value of plus 3. And then if you roll a 5, it's got a value of plus 5. But you can also lose. If you roll a 4, it's got a value of negative 4. And if you roll a 6, it's got a value of negative 6. Now, in the face of this, we want to decide, hey, is this going to be a fair game for us to play, a not fair game for us to play? Are we going to lose money overall? Or are we going to gain money overall? Whether we're lucky or not, if we play enough, how is this all going to work out? The probability, of course, is I'm rolling a single 6-sided dice. The probability is 1 out of 6 for everybody. Now, if I want to do an expected value, which is what part B is all about, I've just finished part A, the probability distribution chart. If I want to figure out what B is, then I have to go ahead and multiply x times p at x in order to get my expected value. Now I can do that in a tabular fashion, okay, by extending my table here and doing a little bit of math. Okay, or what you could do is you could write out the expected value over here. You take each individual value, the positive 1 and the 1/6, and you write that here. Positive 1 times 1/6. And then you add it. Of course, we do order of operations, so we multiply before we add. And then we go positive 2 times 1/6. Positive 3. It's starting to look good for you guys because you're getting lots of money out of here. I'm going to have to go down to the next line here. Positive 4. Oh, sorry, not positive 4. We lose money when we roll a 4. So it's going to be a negative 4 times 1/6, or I guess plus a negative 4 times 1/6, plus a 5 times 1/6, and then plus a -6 times 1/6. That's also where we lose, right, when we have our composite numbers. Okay, and we go ahead and figure out all those, or we can do it in a tabular fashion, which is a little easier. In this case, this becomes 1/6. This becomes 2/6 when I multiply 2 times the 1/6. 3 times the 1/6 is 3/6. 4 times 1/6 is -4/6. 5 times 1/6 is 5/6, and then -6/6. And then my expected value is the sum. So I have to go ahead and add them all up. I add up all the numerators, so they're all going to be over 6. And I go 1 plus 2 plus 3 is 6, minus 4 is 2, plus 5 is 7, minus 6 is 1/6, a positive 1/6. Or if I go ahead and do this, I still will get a positive 1/6. The final result means this. Okay, you are going to, positive means win 0.17, if you round it, cents or dollars or whatever it is that I'm paying you. Let's say it's dollars for more fun. Dollars every roll on average. Now, is that a good thing to do or a bad thing to do? If this was Las Vegas, you would want to play this game, maybe even if you had enough money to front it and you bet it effectively, then you would want to play this game as a career, okay? Because you would be making money eventually, as long as you played for long enough and you weren't really an unlucky person, okay? Because luck is a different situation. But if it was negative, which all the expected values are in Las Vegas, then of course you would want to stay away from that. And really that's the way that they make sure that you leave with no money, okay, as long as you play long enough, and that's why they try and keep you in the casinos. Anyway, here's another example, a lottery, okay, where there's an expected value of your ticket. It's not how much you pay for it, it's a value of your ticket based on the prizes that you could win. Now this is a long and involved process, but it's another good application of an expected value, okay? So here we have outcomes. The outcomes are right here. So that's my random variable x. In this case, it's dollar values, and we're going to want to know an expected dollar value that we get out of it. So okay, it's logical for us to take these values directly. Don't forget there's another dollar value that's here that's $0. We don't include $0 when we do the expected value of the ticket, only because if we want an expected value and we take 0 and we multiply it by anything, it's going to be 0 no matter what it is. So we tend to forget about that situation of not winning anything. So when you look at a lottery, yes, most of the tickets don't win, okay, but some of them do. And it's the ones that do that change the value of the outcome, okay? So it's all going to work into the average, don't worry. So we've got the value of the outcomes, okay, and of course $0, but I'm not going to include that one because it's not going to add to my expectation, and we are going to calculate my expected value because I do have to calculate my expected value. My probability is 1 because there's one $5 million prize, but there's 750,000 tickets, so it's 750,000 tickets, okay? And that's going to be the same for all of these. There's $2 million prizes out of 750,000, and 5 out of 750,000 that are $500,000 prizes, still a good prize. 750,000 tickets, 15 out of 750,000 to win $25,000. To win $5,000, there's 50 out of 75,000, or 750,000 tickets. And then there's 500 out of 750,000 tickets. So it's all the same probability over the 750,000. Now in this case, to get my expected value of this outcome, I take my P at X, okay, that I've created from my number of prizes divided by my total number of tickets, and I multiply those two together. So 5 million times 1 becomes 5 million over 750K. I'm just going to write 750K because I'm going to be lazy. Okay, this is going to be 2 million. 1 times 2, 2 million, all over 750K. This is going to be 500,000 times 5, so 2.5 million, all over 750K. 25,000 times 15, that's 250,000, plus that's 375,000, all over 750K. And then it's going to be 50 times 5,000, which is going to be 250,000. All over 750K. And then finally 500 times 1,000 or 50,000 all over 750K. Okay? And for the expected value, again, it's going to be each of these values added up. So I want to do a sum down here, and that's going to give me my expected value. Okay, you can write it out over there if you want to as well. So I'm going to take 5 million and 2 million and 2.5 million. That's going to be giving me $9,500,000, $9,875,000. 9 million. Let me just add this up the old-fashioned way. And we get 9. And we get 5. I shouldn't do it that way. I should go 0, 0, 0, 0. The 50 and the 50 and the 75. So 0, 0, 0, 5. And then add up 7 and the 5 and the 5 is 17. Carry the 1 times 3, 4, 5, 6, 11. So it's going to be 1, 1, 0. I may have the values off by a little bit. I'm being put on the spot here by the calculation. But if I'm off by a little bit, again, check the calculations that we did. I'm adding up on the spot here. But either way, 10,175,000. It seems close to what it should be. So we got 10,175,000. Okay, is the expected value divided by 750K. Okay, I don't have a calculator close by. I should have gotten a calculator close by. Either way, what that's going to do is it's going to give me an expected value for the ticket. Okay. What I do after that then, of course, is I take this value and divide it by this value, and I get, let's say it's going to be somewhere around, I don't know, $13 per ticket. I'm just eyeballing it. Again, you can look at the calculations that you have in the proper notes that I've given you. I should have a calculator with me, but I forgot to do that. And then I want to go, what is my expected profit per ticket? So what is my expected profit? Well, they sell at $100 a ticket. The value of the ticket is $13, so your profit, quite simply, is going to be $100 minus my $13 gives me $87. Profit. Now, hopefully this is for a charity, or it goes towards charities or any other things that fund, public services like the Ontario Lottery Corporation does. But either way, it would be an $87 profit on every single ticket that was sold. So you can imagine something like a Princess Margaret Home Lottery that had all these different prizes. This is exactly how this prize would work out, okay, based on this idea. Finally, the last one that I have here is I've got all these different pieces of string of 3 different lengths, 153 centimeters, 98 centimeters, and 117 centimeters. Those are my 3 distinct outcomes. I've got 10 of these guys, I've got 7 of these guys, and I've got 6 of these guys. Okay, so what's the average length of string? And then, of course, probability distribution and then average length of string or expected value. So fairly simple, straightforward. So for the probability, there's 10 strings out of a total of 23. So the probability of a 153 centimeter string is going to be 10 out of the total, which is 23. For a 98, it's going to be 7 out of a total, which is 23. And then for the 117, it's going to be 6 out of the total, which is 23. And basically, this is just an average, weighted average, when you think about it. So for my expected value, again, I'm going to take my x times my p at x. So 153 times 10 over 23 is 1530 over 23. 98 times 7 over 23 is going to be 630 plus 56. 686 over 23, if I'm doing that right in my head. Hopefully I am. 7 times 9 is 63. 630 times 56, 630, 56, 686. I think that's right. And then 117 times 6 is 660. Plus 42 is 702 over 23. Okay, this, of course, is my probability distribution. And I can, of course, do a graph as well. But this here, once I add it all up, and I do a sum, okay, then I add up these 3 numbers, and they will be at a 23, and that will give me my expected length of string. In this case, quick addition is not as bad as the last time, as long as my multiplication was okay. 11, 1, carry that 1, 6, 12, 19, and then 19, 18 divided by 23. So that's going to be, about, I don't know what that would be. 2,000 divided by 23 is going to be a smaller value. What is that? I'm not quite sure. Oops, that should be a 2. 29, 18 divided by 23 is going to be about 140-ish, 130-ish. I'm not sure. Anyway, have a look at the solution set and you'll be able to see what the actual values are. Sorry about the number crunching. I'm going to bring myself a calculator for the next time I go ahead and do this lesson. So hopefully that helps with how to do this whole process. Of course, don't forget to look at the beautiful example of the notes that I have there for you. And they've got some notes and ideas and scribbles all the way around it. So check those out and make sure that they work out for you. Talk to you later.